No, I mean, right now.
Oh, I think
he's going to start.
Oh, I see, yes.
And then we'll have to switch.
There's only one, so yes. Okay.
So we might as well just... I have a few announcements before we start. My name is Kaizad Mistry. I'm the short course vice chair for the IEDM this year. And I just have a few announcements before we get underway. First, this short course is being videotaped live. Those of you that have attended IEDM short courses in the past, this is something new. So each lecture will be around 60 or 65 minutes, followed by a 10 or 15 minute question and answer period. The lecture itself will be videotaped live, but the question and answer period will not be videotaped. The second announcement I have is that lunch will be served for all short course participants in Grand Ballroom B. So when we break for lunch, you can proceed to Grand Ballroom B, where lunch will be served. And finally, to get underway, I'd like to introduce our course organizer. We're extremely lucky this year to have Jack Sun as our course organizer. Jack received his PhD from the University of Illinois and has spent 24 years in the industry. Till recently, he was a senior manager at IBM. A few years ago, he left IBM to join TSMC, where he's now the senior director for the Logic Technology Division. Jack is also an IEEE fellow, so please extend a hand in welcoming Jack Sun.
Okay, get this to work. Good morning, everyone. My name is Jack Sun. I'm happy, very pleased to be here to help organize and chair this short course on the future of semiconductor manufacturing. And today we have a very fully packed agenda with 5 distinguished speakers from all over the world to share with you their vision, their experience, their insight into the future of semiconductor manufacturing. As you can see that in the last decade, the whole industry has made tremendous progress in from like a 0.7 micron type of geometry down to right now we are officially into the nanometer era of manufacturing. If you recall, in the VLSI symposium timeframe, everybody changed 0.1 micron into a 90 nanometer, probably for marketing propaganda, but indeed we're dealing with nanometer dimensions now. And there is definitely a lot of challenges and opportunities ahead of us. If you look at the trend and some are reality right now, if you look at the integrated giants like Intel and the DRAM manufacturers, we're talking about gigabits of DRAM and SRAM and so forth. And also the microprocessor frequency has already entered into the gigahertz regime, and they are going even higher. We don't know how we will all make use of that processing power yet, but that's here today. So you're going to see more and more of that. And from a manufacturing side, of course, we can no longer just be content with ppm level of defects. With all these high density of bits and gate counts, we have to worry about less than parts per billion kind of defects. And working with designers, we'll have to really use a lot of design for yield type of discipline in terms of design rules and designs. And if we look at least for this room of people, we are going from just a conventional box CMOS. It still has a long life ahead of us, but in order to boost the performance and to alleviate some of the pain that we may face in terms of transition over to high K, we need all these different device structures that's emerging. And of course, SOI is already in small volume, high-end applications already. And in terms of dielectric, of course, the good old silicon dioxide and the variants of it by introducing some nitrogen for the gate, and also fluorine, for example, carbon for the interconnect materials. They will continue, and but definitely the whole industry will have to work very hard in order to get into the future, continue the Moore's law and the scaling for the nanometer era. On the manufacturing side, you can see right now the fabs are no longer measured in millions of dollars to start up. It's in the billions, and we have already seen the 300 millimeter manufacturing right now coming up into the mainstream. And of course, because of the wafer size, you probably would see fewer of them, hopefully. But of course, for the whole industry, we would still love to see killer applications that would continue this pace to get more fabs built. And in terms of the whole industry, there's also a change from a integrated dominated industry with some foundry manufacturing support for fabless folks. There will be more contract manufacturing that basically integrated guys and foundry folks would have to also work hand in hand in order to provide all the manufacturing services. So this is just a sort of introduction to give you the idea that the future of manufacturing is still very bright, and you can see foundry's share actually is increasing. Now, the challenges and opportunities ahead of us, you can see definitely we have to try to leverage the economy of scale. For example, in the traditional sense, integrated standard high volume products. That's in a little bit of a contradiction with SoC, which we'll get into later. And foundry, of course, by pulling everybody's design together, that's also one solution to this cost issues in terms of getting the economies of scale. Now, mass cost is also increasing exponentially right now. So there's new ideas that will have to be used in order to like cost sharing in the mass and so forth. Now, the biggest challenge ahead of us in terms of manufacturing, definitely in this market, you have to worry about the time to market, time to volume for complex SoC type of designs. You're talking about getting, in 20 years ago, people think about from NMOS to CMOS is a big jump because you have to do all these masking steps to put N and P fabs together. But nowadays, you're talking about with multiple layers of interconnect in the 20s, in the 30s, kind of a masking steps. So we have to really work very hard on the cycle time. And for 12-inch, it's expensive. So some kind of a management on the cost would have to be really thought about. And in the last part of this short course, you'll see the yield and reliability sort of solutions and ideas. Really, we have to use more and more in situ, real-time process control, advanced process control. And this theme will actually be emphasized throughout this course. Hopefully you get some ideas. I don't think we have all the sort of answers to you for the future of manufacturing, but hopefully all the sharing of the speakers will stimulate some thoughts, and we can all work toward a viable manufacturing in the future. And also, in terms of the intellectual property, the building blocks that would have to be validated before you get into a lot of the costly prototyping and manufacturing. Bring up. So this is the list of our distinguished speakers. Bruce from Intel will give you an overview of the overall manufacturing, followed by Rin from Texas Instrument on the front-end manufacturing technology, and Nobuyoshi Kobayashi-san from Solid, Japan, will talk about the back-end. And I do have sort of an announcement here in terms of speaker change because of family reasons, that we'll have Henry Chen from TSMC to talk about 300 millimeter. And PK from PDF Solutions will talk about the yield and reliability. So in a few minutes, we'll get Bruce to start the first session. And there will be a break after this one at 10:30. And then lunch will be at noon. And after lunch, we have 2 sessions before the coffee break at 3:45, and followed by the last, but not the least, important session on the yield and reliability. Now, as Kaiser had mentioned, this is the first time, actually, we try to do the videotaping live. And because of that, we will ask for a little bit of your cooperation to avoid lengthy questions during the talk, if you can hold off till the end. We'll try to have each speaker spend their first 60 minutes on their presentation, and then reserve for the last 10 to 15 minutes, in case they run over a few minutes, for the Q&A. And if you do need to ask a question, please use the microphone so that everybody can hear, and the speaker will not have to repeat. And only the audio part will be taped. Whoever asked the question will not be on the screen. And so I think this is the meeting logistics. Now, I'd like to quote actually Paulo in the ITRS sort of committee, that everybody is afraid of this red brick wall, but in the roadmap. But I think with the smartness of this whole audience and the whole industry, I think we can pull it off. And hopefully we can extend this wall further and further out. And so I'll stop right here. We would like to introduce the first speaker to talk about the overview of semiconductor manufacturing. Bruce, you come up. Bruce Song is currently the Fab 11X manager of Intel's first 300 millimeter semiconductor chip factory. He has a lot of experience at Intel in the industry, and he's also an executive board member and a technical chair of International Symposium on Semiconductor Manufacturing. And he serves on various IEEE sort of functions, and he's now IEEE Electronic Device Society Manufacturing Technology Committee, and is a certified journal from Abraham go. Yeah. So I'll stop right here. It's as long as you can read there. Okay, so.
Passing of the mic. That's all the viruses that are in my presentation, I guess. So I want to start off by thanking the IEDM coordinators for inviting me to speak to you today. Especially want to acknowledge Kaizad and Jack. It takes a lot of effort on their part throughout the year to pull together a course like this and to participate in the activities of IEDM. And I just wanted to acknowledge the hard work that they've done. Meanwhile, they do have normal jobs, so it makes it especially challenging. Today I'm going to talk to you about a few things. I get the advantage of doing a overview, so I get to talk to you a little bit about everything, and you'll get to see more details in the subsequent presentations. Initially, I'll talk to you about some of the business trends. These are the driving forces, why our industry exists, why we do the things that we do in the first place. Certainly, we don't create products just for the sake of creating products. We create products because there's somebody out there who wants to use these integrated circuits and advanced capabilities. Then we'll move into new technologies, which talks about how we do the things that we're doing. In particular, some of the key enablers which will allow us to make and introduce even more advanced products and provide better services to our customers in the future. Manufacturing capability, which are really the next three sections talk to manufacturing capability and the way in which we will make not just one or two of these particular devices, but tens of thousands, perhaps millions or even hundreds of millions of particular devices. And manufacturing capability, there are a number of manufacturing sciences that are being applied. The conversion to 300 millimeter, which enables the industry to do far more with far less. And supply chain management, which really improves the efficiency of the entire supply line from the beginning of materials procurement all the way to supplying materials to the end customer. So, starting off with business trends, oftentimes we see two different versions of these prediction charts, one from the SIA, one from the VLSI research. This particular chart places both of them next to each other. I find it kind of interesting how well aligned in general these two organizations are, at least out until 2005, when you see a little bit of deviation in terms of their prediction. Clearly what is most obvious on here is in 2000 how we have just come off of what is the largest recession in the industry's history, at a 30% drop in terms of sales between 2000 and 2001. We're really still feeling this, even with only a couple of percent growth this year. I think many of us hardly notice that any growth has occurred, perhaps between the last 2 years, that there's still significant struggles, some consolidation that have been going on in the industry, and a lot of challenges, as Jack pointed out, some of the movement from IDM manufacturing into the foundry business. Into the future, over the next couple of years, the prediction is more robust growth, about 20% each year. Of course, the future always looks the best when we are sitting back here and looking forward and trying to predict what it looks like. So hopefully their estimates are relatively good, which bodes well for our industry and bodes well for the products that we will be manufacturing. So what do people do with these particular products? If you go back to the 1950s, this is a chart put together in Japan by MIDI and enhanced by Panasonic. In the 50s, basically the only electronic components that were being bought were radios, transistor radios, and 100% of all the electronics that were made basically went into those radios. And since then, over subsequent decades, came televisions, first black and white, then the colored televisions. Then came the VCR, which helped us contain and get some of the control over all this information that was coming to us. And then in more recent years, into the 1990s, we've seen the fantastic growth of the personal computer, and now really the onslaught of cellular telephones and personal digital assistants, which now put a lot of the capabilities that we had many years ago into our hand with a whole fresh new way of dealing with them and making them far more personal than they were back in the 60s and the 70s and so forth. Panasonic goes on to point out that they believe that the next growth into the future are going to be these digital audio video products. Things like HD TV that we've heard about for many years. We've known technologically the capability existed, but there was no infrastructure out in the world. There's still very, very little infrastructure for HD TV. But once we start to deploy that, what we are essentially saying is that we expect the entire world to replace all of their television sets, for that matter, all of their audio devices with things like MP3 players over the next few years. That has to drive tremendous growth in our business, has to drive tremendous amount of silicon needs, has to drive the improvements in both our manufacturing capability and the technologies that will be used to make those. We have to make them effective, and we're going to have to make them very, very cheap. Needham & Company looked at it in a slightly different manner. Here you can see their prediction in their application, personal computers over a couple of years, and you can see that their actual prediction in growth is also a large amount in this consumer products region, which would include the HD TV. But you'll also notice that they have a lot in the other category, which they put in things like industrial uses. Many of the industrial products that we see in the world nowadays are still using fairly old technology from 20 and 40 years ago. A lot of industry has not modernized yet. There are still many opportunities. Another thing that goes into this other category is the use for defense related technologies as well, and certainly we have seen advancements on that front in recent years. So what kind of devices will we actually be making in order to put into these products? What are the things that, from our business, what will they look like? Well, you can break it down. It's on its own. You can break it down into, how far back did we go? Into a number of different components here. And you can see how the devices divide up. On the bottom here are the MOS, the logic devices, primarily logic only, but certainly what we're seeing in the future is growth in integrated devices that will permit us to have more and more different kinds of capabilities on fewer and fewer chips. And we're going to see continued growth in this arena as we have over the past years. That's also where all the digital technology, HD TV, for example, all falls into that. Most of the cellular telephone falls into that sort of category. You can also see nominal growth in some of these other regions, but the key thing is that you can expect to see us growing from this, where we are today in 2002, to roughly doubling the output between now and 2007. So, the way in which we put this together, as we know, has been a complex and continuing process of improvement in our technology. A number of different advances, hunting for that brick wall that Paolo referred to when Jack quoted him earlier. Here is kind of the result, if you will, of Moore's Law. The top graph here plots out the individual nodes, and you can see individual products that have been manufactured at these nodes over recent years. The lower graph, the lower line actually depicts the smallest distance, the effective channel, the channel lengths that we are seeing as we produce these particular technologies. So for example, a 130 nanometer technology node is not manufacturing devices that are running with smallest details of 130 nanometers. They're really running with channel lengths of about 70 nanometers, so considerably smaller. And we expect to see this trend continue. What you're really seeing is an acceleration over several technologies, as we've seen the deviation between what the smallest physical geometry is and what the effective channel length that we are seeing in those logic devices. This has also been updated since the last time this was presented. A couple of years ago, we really talked about 130 nanometer really being in development. Now 130 nanometer is solidly in manufacturing. Many companies are producing at the 130 nanometer technology, and many companies are looking to 90 nanometer technology next year. So clearly we are in the development phases there and advancing the research out a couple of generations beyond this. Moore's Law has really been the drumbeat to which the industry has continued to beat over several decades, and the result of that has been that devices have gone from manufacturing just 5 to 10,000 transistors to what will be over 1 billion transistors on a single device the size of our thumbprint within just a few years. Clearly that capability will exist this decade, and clearly the demand will be out there for us to continue to tap into that particular technology. So what's the official roadmap look like? Well, if we look at the ITRS from a lithography perspective, we can map across here the various years. The logic pitch, DRAM half pitch really dictate the technology node. The definition of the size that we are typically at when we achieve a particular technology. The gate we can look at, the contact resistance, and the overlay, the registration that we see down here. And this is the roadmap by which our technology beats. This is really what enables Moore's Law to continue to exist, is if we continue to march down this path, we will continue to perform and accelerate along Moore's Law. Now the fascinating thing about, or one of the things that I find fascinating about this particular chart, is that our industry tends to put up roadmaps like this without a clue about how we're going to do some of this. So if you looked over, for example, so these last couple of columns, and you said, now how are we going to do that? How are we going to do just the line width element of it alone? We really don't know the answer to that. We have some ideas. We have many proposals. We have some theories about how we might achieve some of these smaller and smaller physical geometries, but we aren't absolutely certain. We are still working on that. And that's to say the same thing, by the way, if we went down, we looked at putting in unlanded contacts, for example, or developing these kind of overlay dimensions from a lithography perspective. We don't have scanners, steppers that can do this kind of capability yet. This is the challenge for the industry. This is what we put up in front of us. Now the fascinating thing, of course, is for those of you who've been in the industry, you know that 10 years ago we had this same kind of roadmap. And I could have said the same thing then. It was not clear how we were going to achieve the things today that we have achieved today when we were predicting it 15 years ago. But we've managed to do it. We've developed the technology, we've developed the capability, and we are manufacturing. Again, this is not academic research where we theorize a possibility. We are actually manufacturing tens and hundreds of millions of devices at technologies that we did not originally think were capable at this time frame. Now, this is the lithographic challenge. This is really what the major challenge has been in our industry over the last decade or so. It was simply scaling it down, getting smaller and smaller geometries, getting smaller and smaller line widths, using smaller and smaller wavelengths of light and so forth. But our challenges into the future are going to be far different. In the past, a transistor largely looked the same. For many years, we have used basic silicon substrates, doped for N-channel or P-channel transistors with largely the same kinds of dopants. We have used largely the same kinds of dielectrics, silicon dioxide for the most part, in developing ours. We've used largely polysilicon gates in most of the devices that we've been manufacturing. Up till a few years ago, most of the interconnects were made of aluminum, and now many of them are being made of copper. Okay? But there's been a large uniformity in terms of the kinds of materials that we have been using in the past. Like I said, our major challenge was the scaling. Scaling from 2 micron to 1 micron to a half micron and now into the 90 nanometer geometries. But for us to move forward, we're going to have to work on a number of other different areas. So in order to improve the speed of the devices, we're going to have to continue to refine not just the physical geometries, but the effective geometries that exist on our devices as well. So we have to control the LEs. We're going to have to change the way in which the electrons or holes move within the bulk materials, affecting the mobility. The interlayer capacitance, which didn't used to matter when we were using large scales, now matters as we are using smaller and smaller geometries. They're getting closer and closer. The capacitance is changing dramatically. The metal lines, the contacts, whether those contacts are down to silicon or they're contacts, vias, if you will, between metal layers. The gate is going to have to change. We now count the gate thicknesses using individual atoms. A change in a few nanometers is a change in the number of atoms that we are essentially measuring. We are measuring at scanning electron microscopy levels. We need to control that. One of the biggest problems is making sure that we don't get leakage just through the gate. Remember, it's supposed to be a dielectric. At the regions that we're talking about now, it actually has conductive capabilities, tunneling, if you will. We have to work on the gate depletion, the inversion, the way in which the electrons are moving underneath the gates. We're going to have to look at leakage, whether the leakage is in the channel between the sources and drains or between adjacent transistors, the isolation of those, or down to the substrates. Regions that didn't matter when we were talking about 1 micron technologies now matter as we're discussing 90 and 65 nanometer technologies. And the dopant profiles, where and how we place the various atoms individually in the devices, how they are positioned on the substrate, how they are activated. They must be in exactly the right place, in the exactly the right state, or they won't function the way we expected them to. Again, these are things that didn't matter a few generations ago. Now they're things that are the real challenges for us to go forward. So the response to that is going to be a number of different technologies that you'll hear talked about over the next several presentations. One of those, for example, is SOI. Instead of building our devices on top of what is, in a relative sense, a very large substrate silicon region, we can build those on top of insulators. So we can control the depth to which we are getting conduction and flow of electrons and so forth in the bulk, and how that is affected. We will need to add high-K gate dielectrics. I mentioned the need to ensure that we can not get tunneling, not get conduction through this dielectric. We're going to need to use higher K gate dielectrics in order to achieve that. Silicon dioxide is running out of steam. It's run out of the number of atoms. If we are going to continue to make our devices function at reasonable electrical fields, then we're going to need to change the films that we are using to build the transistors. The gates themselves will also need to be changed to alter the work function the way in which the devices work. We can use strained silicon, a technology relatively new, very new, just being introduced into manufacturing over the next year or so, to alter the way in which the electrons move, the lattice in which the electrons operate. We can alter that lattice, and in doing so, improve the mobility of the electrons within that lattice. The contacts are going to be changing. We're doing more and more of the unbonded contacts. We need to make sure that we don't end up with junction type problems as a result of the contacts and the new materials that we're using. We'll use low-K interlayer dielectrics, the layers between the aluminum or now mostly copper lines on the advanced logic devices. As we've got to higher and higher currents, smaller and smaller geometries and spaces between the metal lines, the traditional silicon dioxide and direct derivatives from silicon dioxide have been problematic for us and are creating issues. And so we will be altering that using low-K dielectrics in the back end. And then also just seeing improved conduction from those metal lines. We have seen more and more movement to the higher conduction copper interconnects from the aluminum. And I expect to see that and variations on the copper interconnect thing continue into the future. The architectures themselves will also have to change. I showed earlier a very standard metal oxide semiconductor transistor, very traditional type of design, but even it is running into limitations. And we've seen a number of different devices proposed and will be talked about certainly at this conference, have been proposed at this conference in the past. One of them, a depleted substrate transistor, instead of building the transistor on this large bulk of silicon, controlling the body, the depth, the bulk region with a very thin silicon body. Other alternatives, looking at a FinFET, where you have a gate that actually is running on both sides of the channel. Or you can end up with a tri-gate configuration where you've really got the gate wrapped all the way around the channel area and gives you 3 different directions from which you can create the electrical fields. There's certainly going to be changes in the way we build our devices. Again, our problem is not one of simply scaling down the smallest geometries that we've been working with over the past. It's not simply making things smaller. It's going to be changing the fundamental way in which we make them. Different materials will be used than we have had in the past, as will different structures than we have dealt with in the past. All of these will bring new challenges to us in the future, but all of them help us move that brick wall out a few more years and enable us to continue to manufacture in our industry. So how do we actually go about doing this? I mean, making 1 or 2 of these things is interesting, it's fascinating, but really what provides the benefit to consumers, what provides the benefit to society, is when we can put it into a product where we can make something faster so that the software guys can now write more complex code, and where once we had to type in, we are now using mice, and where in the future we will be talking into computers, for example. All of that capability comes because we are able to actually manufacture products, make something that is useful that will be introduced into the industry. And in many industries, manufacturing has changed very little over time. But in our industry, we've taken advantage of a number of different sciences, manufacturing sciences, to improve the capability as we have moved from 1 micron technology up to what is today the 90 nanometer, or moving into the 90 nanometer technologies. We've added a number of different capabilities, each one improving the process control, improving the parametrics, improving the capability on the manufacturing front. So if we look back when we were working on 1 micron technologies, we just simply put in simple shop floor control systems. And then largely out of the automotive industry and other industries, we were inspired to apply simple process control to improve the distribution and the variation that occurred. And then we've added in a number of additional controls. Advanced process control that integrates things. I'll show you some examples of that. We've improved the data flow within the factory so that we can enhance the ability, the operation, and the flow of materials inside the factory. We're working it up and down the supply chain. We've put things on the internet so that they're more accessible not only to our customers, but also to our suppliers, improving the entire data management flow and making it remotely available. We've come back and we've integrated yield management in. Process control, advanced process control, has existed in our industry for more than 10 years, but we don't stop with just the minimal capabilities down here where we were at the 1 and the 3/4 micron generations. We'll continue to improve those, and no doubt we will continue to improve them into the future. Some of the real challenges, however, have to do with our ability to get and access some of the automation standards that exist out there. As we move to 300 millimeter wafers, we now find that it's not only important to control lot-to-lot variation, but we have a much greater need for wafer-to-wafer control and within wafer control now that we're putting so many devices on a single wafer. We really need to have some additional standards that need to get deployed across our industry. All the equipment sets need to be able to have this capability. It was having these standards that enabled us to get to 300, having some standards that enabled us to get to 300 millimeter in the first place. It's continuing to have these standards that'll be necessary for us to move out into subsequent generations. So let's look at some examples of process control and the variations on process control. One of them has to do with fault detection capability. Fault detection is the ability to identify when something goes wrong, a fault, when we have an issue. A tool doesn't perform the way we expect it to, and it's generating material that is different from the way it used to be. Or it is expecting to generate material that is different in the future because of the wear and tear that's going on, or the way in which the chamber is aging, or the materials, the targets, and so forth are aging. Over here we show a graph of the benefits over time from the various different technologies of applying fault detection capability. And this is really just looking at purely line yield and the benefits that we've seen as a result of applying fault detection capability throughout the process line. And you can see that it has been dramatic, and certainly as we get more and more devices, more and more capability on a single, now larger wafer, the paybacks are larger and larger out into the future, and that will continue. Certainly the plan is to deploy 100% fault detection capability on all process tools, and we believe we're within the capability of doing that on the 90 nanometer nodes. This adds a lot of benefit to our technology. It adds the benefit in terms of improving the yields. It adds the benefit improving the cost structure under which we operate. Our industry, like most, the expectation is they want more for less, a higher value. And in our industry, it's an especially steep curve. And fault detection enables us to continue to improve that from a line yield perspective. If we look at process parametrics, one of the capabilities is to look at advanced process control within the process line. And here I depict a capability utilizing the patterning processes within the semiconductor process flow. So if we pattern, for example, on a stepper, the wafers move on to a SEM where we can then monitor the CD performance that actually came out of the stepper. The information is then fed through a computer, fed forward to the etch operation, and you can actually adjust the etching parameter based on the information that came out of the stepper as read in the CD SEM. Similarly, the data flow out of the reg monitoring tool can be fed backwards to the stepper, and adjustments can be made there. And again, we can take information after the final check operation beyond the poly etch and feed that as well back to the stepper and adjust the exposures there so that we can alter based on etch bias. This is an example of advanced process control internal to the process flow. Now the enabling, what this does is enables better performance, better parametrics, tighter distributions from the typical process flow that we get within the factory. So if we looked at a particular example here of just the registration feedback monitoring, on the right-hand side, this is without advanced process control applied. This is the amount of error that we see in the registration that we're going to have to deal with. Something that's not only complicated at an individual particular layer, but if it's early enough in the process flow, can also affect subsequent layers. You can only control as good as your upstream layers have been controlled. But if we apply advanced process control, as I showed on the earlier slide, you can actually reduce that error down, and you can also see that the distribution is also tightened up somewhat as a result of this as well. Advanced process control affords us the opportunity to identify where systematic variation exists and permits us to control that systematic variation. The things that we know about, we should try to control. APC enables us to do that. A second example is here. This is end-of-line performance as a result of advanced process control being applied during the formation of that poly gate. This is an example of looking at speed bend frequency of an advanced logic device. And the yellow line depicts without advanced process control. The red line is after we enabled advanced process control. And you can see two things here as well. The speed has gone up and the distribution has become tighter. Again, the result here is an improvement in parametrics, an improvement in speed, a tightening of the distribution, which is an improvement in quality, and a benefit that we can really give to our customers in faster parts and better performing parts. If we look at the application of feed forward and feedback as we've been applying it, you can see how we've been applying more and more advanced process control with each different technology. Applications are applied anytime we identify an opportunity to capture systematic variation, and we can figure out a way in which we can apply it. We will continue to do so. So regardless of whether it's a lithography one, which is the example that I showed you earlier, and certainly our biggest opportunity, or the place where we have applied it most readily, you can see that we are applying it across a whole host of applications in the technology, and continue to do so over the lifetime. This isn't something that you stop just when you in the development stage. This is something that we continue to do as we again identify systematic variation and seek to eliminate that variation as much as possible. This is fundamental to continuous process control. This is a whole couple of generations beyond the traditional ideas of statistical process control. Far more sophisticated, far more capable, things that are enabled by the automation systems and the data and information that is provided to us by not only the metrology tools, but the process tools themselves. This application of advanced process control all talks about control within a given factory. Another application that we can look at is the copy exactly method, a technology that Intel has been using now for more than 10 years, quite successfully to match technologies between different factories. So instead of going to a customer and saying, here's one factory, here's another, and the customer says, well, two factories, I've got to qualify them differently, we simply demonstrate that we run copy exactly between them, and they see us as one particular company. That obviously has some benefits on the back end, but the front end of it also enhances dramatic process control. By identifying and ensuring that we run with the same physical inputs, we end up with statistically matched responses. The outputs from the technology are also the same. Control the inputs, we get controlled outputs. We keep matched throughout the entire technology, coordinating the changes, doing various audits, monitoring the process control systems, and having good forums in which we can communicate. At one time, all we did was control a few different parameters. Now it spans an entire suite of virtually every parameter, whether it's within the fab or the things that are feeding, whether it's materials, raw materials into the fab, or the continuous materials such as things like water or the air that's going into the facility. The benefits of Copy Exactly are really quite dramatic. Copy Exactly facilitates a significant amount of innovation. It eliminates the risks. We position ourselves in a way in which there are not a large number of variables. In fact, the idea is there are no variabilities between the factories because we are copying the technology exactly, doing things the same way in one factory that we are doing in another one. This is really important, even more so now that we are down at 130 and 90 nanometer technologies. There were a few generations ago when if you were off by 10 or 20 angstroms, 50 angstroms maybe in a particular film, it didn't matter. There were a few generations ago where an extra few particulates didn't matter that much because of the way they laid down on the wafer. Or the size has changed, where once we were concerned about a 1/4 micron particulate, now we're talking about 0.01 micron particulates having effects. Things that didn't matter in the past matter more now. And it simply underscores why Copy Exactly is even more important today than it was 5 and 10 years ago. Small deviations in process module can really have a significant impact in the yield or parametrics. Very, very small deviations. Remember, the materials that we were talking about, we are measuring individual atoms in many cases. Atoms in terms of the layering of, say, the gate dielectric, or atoms in terms of their position on the silicon lattice in the channel region, for example. Copy Exactly also enables significant improvement within the corporation by leveraging multiple engineering organizations. If you have exactly the same process in one fab as you have in a second fab, one fab can use its engineering organization to work on one problem, another fab can use its engineering organization to work on a second. Because the processes are matched, when both engineering organizations have identified the solutions, it's directly applicable to the other facility. That essentially doubles the rate at which we can identify and continue to improve our technology even after the development has ceased on a particular technology. And it also enables our ability to advance and to start up new technologies. It's something that allows us and gives us significant confidence so that when we design a technology at Intel up in Oregon, our ability to transfer it down to, say, my facility in New Mexico, our confidence is extremely high because of the application of Copy Exactly. If I look at the rate at which learning has improved, back in the late 80s, Intel did not really use much, if any, Copy Exactly type of technology. We have used Copy Exactly with successive additions of the capability throughout the 1990s and continue to do so. And you can see the rate at which the defect densities have come down on each of these subsequent technologies. And this year showing, for example, on 300 millimeter, how we're also able to apply it not just, or to apply it on the advanced technology. Again, the second fab is able to start up with exactly the same process, the exact same parametrics, and first silicon out of a new fab looks absolutely identical, performs the same, and yields the same as the material out of the initial factory that has done the development and is transferring the technology out. We can also see the effect of ramping and why its leverage is so important when we consider that each subsequent technology we end up producing more. Customers have demanded more and more units each year since the beginning of our industry. You can see how we are applying how the acceleration of the various different technologies has occurred from the beginning of a ramp to the end of a ramp. This is critically important for us to capture good yield and good performance early on in a ramp, because if we don't capture it early on in a ramp, we are going to have to deal with the reduction in the cost, deal with the reduction in the sales prices and so forth that occur later on in a technology. So yet again, the multiplicative effects of having matched parameters shows it's important through these growth rates in subsequent technologies. It prevents us from losing opportunity cost. The finance folks would talk to us about the opportunity of gaining more, whether it's market share, more sales, but more revenue. Copy exactly, when mapped to advanced technology, essentially helps to ensure that we don't put ourselves in a position of losing opportunity cost. We actually are able to leverage it. So copy exactly helps to ensure that we do this from a parametric sense. Of course, designing the fab also has a lot of benefits and importance as well, because really what we're trying to do is provide to the customer the kinds of products with the features that they want, while maximizing the output of a given facility, minimizing the cycle time, which generally means minimizing the inventory that's actually sitting in process within a factory, and doing that with the minimal amount of costs. Now in our industry, because we are so defect sensitive, that cycle time parameter really has more than one benefit. It's not just cycle time because it gets it to the customer sooner, it also reduces its exposure to any environment during the sensitive processing flows that occur inside of the clean room. It means we get less defects, and if we get less defects, we get more units off of the wafer. It costs the same essentially to manufacture a wafer with few defects on it as it does to manufacture one with a lot of defects on it. But the sales, of course, that we generate off of the one with few defects on it is dramatically larger. Capital purchases are also really critical, with factories costing $2 and $3 billion each, and with the capital portion that's going into our wafer cost being roughly half of that, it's really important that we minimize capital purchases. And so some of the ways in which we apply advanced control and manufacturing science capability is not just in the process flow, but the way in which we identify improvements within the factory. And we can use our own technology, the computer systems that we make, to produce simulations that can help validate how we design and put together a particular equipment set. So here's an example of a factory that has been put together to run a large volume of material. And we've gone out and we've simulated the purchase of equipment, and we have simulated the way in which it would run, and we put it through a dynamic analysis, and we run it for many, many weeks. Okay, actually many months. This represents about a year's worth of data that is up here. And if we look at the output from a factory like this, you might see this kind of performance in terms of the output that is generated in terms of wafers out of the factory. And what you probably will notice is a large amount of variation here. You might even, if you did an average, you might say, well, the output is actually on a slight downward trend even in this factory. That's probably not something good. You don't want to slow down the output from a factory. You'd like to at least maintain the output or perhaps accelerate it. Well, if you are slowing down and you continue to start material in the factory, you would also expect to see that the speed, the average time that the wafers spend inside the factory is probably going to go down over time, and eventually to a critical point at which you're really going to have to do something significant in terms of the way you operate the factory. You're either going to have to stop starting wafers, which means you'll have to stop shipping some wafers or slow the shipment of wafers, or you're going to have to go out and buy some more capital equipment. Now, what simulation affords us to do is allows us to take the same pot of money that was used to buy equipment in the previous example, and instead of using traditional techniques in terms of the way we apply the money throughout the factory, we come up with more optimized ways in which we run the factory. We can get an output profile that looks like this, and if you compare it with the previous slide, I think you can readily see that the variability has gone down dramatically. You can also see that the output is increasing in this particular factory over time, has a clear upward slope, which means that the speed of material, assuming you're doing the same starts each week, is accelerating in the factory. We're getting the material to the customer sooner. And of course, if we're getting it to them sooner, they're paying us at the current prices, not the reduced prices that will occur out in time. And if it's less time inside of our factory, we get the improvement in terms of higher yields, and we can improve quality by having faster information turns in the factory. Again, this is an application of using process control and manufacturing science to understand how to design a factory using the kinds of technology that we happen to have. 300 millimeter is a whole nother step. The semiconductor industry conversion to 300 millimeter is the largest, most complex, and most costly retooling of any industry in history. Think about any industry and the retooling that they have done. And nobody has gone through the same kind of conversion that we are in the process of going through now and over the next few years. It has a dramatic effect. If we look, for example, at Intel's deployment of our 130 nanometer technology, you can see how it takes us about 5 200 millimeter fabs and a portion of a couple of 300 millimeter fabs for us to generate the number of devices that are necessary in order to support the market. And you can see the ramp over time. If we look at the 90 nanometer technology, however, you can see that what was once done with 6 to 7 factories at 200 millimeter is really done almost completely with 200 millimeter, with 2 300 millimeter factories and a little bit additional from a third 300 millimeter factory that we'll be bringing up in Ireland. The leverage is incredible out of 300 millimeter. It's a trend that we've been on for many, many years. We have doubled the area that we are processing on roughly every 10 years. But this is the first time that we make the step in terms of doubling from one wafer size directly to another. Subsequent doubling of the wafer size has required subsequent numerous changes in the number of wafer size transitions that we had to go through. This time we get 2.5 times the output by doing a single transition from 200 millimeter to 300 millimeter. And this prediction from VLSI Research essentially says that roughly half of the world's silicon will be processed on 300 millimeter within about 5 years. And I think that that's clearly a trend that we will be headed down. And if demand does meet the expectations as was shown in the earlier slides, I think the industry will be positioned to at least move at this rate. I think that we'll also accelerate as more material is moved from IDM manufacturing to the foundry business as well, as the foundries are starting to put more and more of their silicon on 300 millimeter, especially over the next year or so. Now, with Moore's law that talked about the reduction in the size that was going to occur in the small features or the advancement in terms of the number of transistors you could get out of a given area, there's been kind of a corollary that says that at the same time we're going to be doubling the cost of the facilities in which we make the factories. So back in the 70s and 80s, it might have cost $10 million or so to build a manufacturing facility that could generate the products that were needed. Nowadays, the number is $2 billion, $3 billion, and when we get into the advanced lithography techniques over the next couple of years, we're going to see that price continue to accelerate. So the costs are going to go up dramatically, but the paybacks are going to be incredible. We obviously know that the ability to ramp a 200 millimeter factory compared to a 300 millimeter factory is more than twice the rate. If I add 1,000 wafer starts a week or add 4,000 wafer starts a month to a particular 300 millimeter factory, I will get roughly 2.5 times the output as a 200 millimeter factory. One 300 millimeter factory is ramping at the rate as 2.5 200 millimeter factories. The leverage, the ability to bring our products to market goes up dramatically simply by applying the 300 millimeter conversion. And when you apply a 300 millimeter conversion on top of Moore's law, the conversion from 130 nanometer to 90 nanometers basically means that we are going to see more than a 4-fold improvement in terms of the transistors that we're going to put on a wafer. A 4-fold benefit that goes to our customers. The benefits aren't just an output either. The benefits are in terms of the usage of materials and the way in which we process and the emissions that come out of our factories as well. We can expect that the typical 300 millimeter factory will generate roughly half the emissions that a same product would have been had we generated in the 200 millimeter factory. The wafer usage that will, the water usage that will be used on 300 millimeter wafers will also be roughly half of what it had been if we had used 200 millimeter wafers. This is a tremendous benefit. It's not only a benefit because of the materials, of course, that we're using also go down as proportionally as well, but it's also beneficial in terms of the effects on the environment. It makes us more responsible as an industry and makes it easier for us to continue to manufacture as we move forward. The factories that we build in are also changing. We're going to see an example of this with TSMC in a couple of presentations as well, where they show their factory. This is a cross-section of Intel's 300 millimeter factory, very different from our 200 millimeter factory in a couple of different ways. You can see, for example, the large stockers in the middle of the factory. The factory was built with a much larger center, the backbone of the factory, than was our 200 millimeter. In fact, to go beyond that, 300 millimeter was the first time Intel decided what we were going to build inside the factory and then decided how to build the factory before we actually built it. In the past, we had built a box and then figured out how to put whatever wafer size or whatever technology into it. With 300 millimeter, it's far more integrated. We knew what was going to go in it before we began to build the box in which we were going to build the factory. It's also fully automated. The clean bays, we have material delivered to them through an overhead hoist vehicle system. And the main aisles, we have an interbay system in which we move material between bays from throughout the factory. All of that serves to speed material. It also serves to give us far better control over where material is and how it's being processed. The layout in the factory also changes considerably. In a 200 millimeter facility, Intel was operating with a very traditional bay and chase operation, and it was very much a bay-centric facility. We wanted to position it in such a way that an individual technician could stand in a place and operate several tools simultaneously. So we wanted to make sure that that person could turn around and operate all of those tools easily from that bay position. With 300 millimeter, however, because all of that material is automated, what's really important is to facilitate the design from the chase area, because instead of technicians moving material, what technicians are doing are working on the equipment. They're maintaining the equipment, ensuring the equipment performs at the performance that it's designed to, and ensure that its uptime is as high as possible to ensure that we're getting the maximum output so that we don't have to go and buy more and more material. Intel's 300 millimeter facility layout is also changing, and what we're seeing with our subsequent generations is also moving to the more common ballroom style factory away from the bay and chase, but still designed from the equipment maintenance perspective, not from the operations perspective. And with automation comes the ability to enhance our ability to operate the factory as well. Traditionally, there were no command centers. One tool, one monitor, one start button, one monitor and set of control charts, all on one panel. If I wanted to work on multiple tools, I had to walk from one tool to the next, and no matter how close they were, I was still dealing with a non-integrated system. What 300 millimeter and the more advanced capabilities do is now affords us the ability to have command centers, which we can place in a variety of different locations that make it easier for us to monitor and control multiple tools. I can monitor the performance and compare what is happening in one tool with what's happening in another tool. Again, I can use that from an advanced process control perspective to eliminate systematic variation, the variation that perhaps is occurring through tool-to-tool performance, and I can deal with it from a centralized command center, operating multiple tools, perhaps an entire bay, or maybe even multiple bays, and perhaps even outside of the factory, and perhaps someday from wireless devices as well, so that we're not tethered down to any particular terminal, whether that be inside the factory or outside the factory. So the combination of all this means that the economics of 300 millimeter are very, very positive. What you see here is the capital cost per unit area of silicon, and because each technology adds a few more mask layers or a few more implants or a few more films or requires us to add metrology to improve the process control or to eliminate a few more defects, you can see that the cost has improved from the 0.35 micron down to 130 nanometer technology. But the step from 130 nanometer, 200 millimeter to 300 millimeter essentially reverses that cross trend. Takes us back to where we were roughly 10 years ago in terms of the cost per silicon area. Again, the result of the increase in wafer size, the control of the capital costs, the reduction in the raw materials that are being used, help to ensure that the costs that we actually attain generate the 30% cost entitlement that was expected by organizations such as Semitech or Salit that were predicted as we converted from 200 millimeter to 300 millimeter. It also affords us the ability to integrate more things, larger wafer size, more automation, more advanced process control, more use of technology within our factory. All of that integrated together gives us the benefits, not just of the sum of each of those individually, but the integrated effects of all of them compounded on top of each other. Provides a safer environment with less variability, less latency in the supply chain system, and more control, providing better output with better performance. From a supply chain management perspective, looking at the control of material flow from the very beginning of a process flow to the end also has identified a number of opportunities. I remember back 20 years ago when the automotive industry used to come to us and they used to tell us about how we needed to control the materials that were flowing into us. And they were telling us that that was important because they wanted to ensure that the materials that they were getting were of the highest quality and had very tight distributions. Not only were there no failures, but there wasn't a large amount of variability. Well, that's something obviously that we need in our industry as well, and things that we are doing more and more applications of nowadays. The specifications for the materials are tightening down. Again, what used to be satisfactory to quarter micron technology is no longer good at 90 nanometer, and certainly will be even more of a problem as we get below 90 nanometer technology, and we're using more and more exotic materials, and those architectures that I showed you earlier become more and more commonplace within our integrated circuits. Process control is going to have to continue to get better. Not talking about the process control of the parameters we have internally, but the process control of the silicon substrate that we get, the process control of the various acids or solvents and other chemicals that we deal with, gases and so forth. The process control is going to have to be considerably more robust. The data transfer is going to have to improve. Remember, we talked about advanced process control within a process. What about the advanced process control from the materials that we actually receive? What would we do if we knew that the conduction, the bulk characteristics of our silicon, or the epi on which the silicon is grown, is a little different on batch A versus batch B. Would we do something different inside of our factories? I think in the future we will need to do that, and certainly must have the capabilities to do so. Short lead times to reduce inventories. More and more we find that costs are proportional to the inventories that we hold. Costs and defects are also proportional to the length of time that inventory is held. We need to be reducing that down as well. And then, of course, having worldwide distribution, as we're now starting to see factories come up in more and more places around the world. The equipment supply chain is also going to have to improve. Process specifications, that's why we buy the equipment, to put down the films that we need. The film control has to be better. The defect count has to come down. We have to have high tool performance. We can't continue on this trend of ever increasing multiplicative effects of the cost without getting improvements in terms of the availability and the performance of the equipment itself. And they must be fully production ready. The ability to apply advanced process control capabilities, to integrate the diagnostics, to provide us more information on the inputs so that we can control those, monitor those, control those, and provide the necessary outputs. All of this serves to enhance our ability to improve, bring new products to market faster, to design them faster, to put them into our manufacturing lines. We're going to have better and rapid mask making capabilities that are going to generate the products that we need out there, and to be able to do that under very good cost control now that the mask cost has also become a significant portion of the design. The cycle time for those initial product introductions will have to come down further. Roughly would estimate somewhere in the neighborhood of a half a day per layer, so that we can get our products out to into first silicon as rapidly as possible. And there's a number of different techniques for doing that that have been reviewed. And process integration will continue. More and more advanced process control, feed forward, feedback mechanisms, all of that with the intention of improving the output of the systems, producing higher quality products, tighter parametrics, and high volumes. So in summary, consumers are going to continue to want more and more technology. If you tried to log on to your company's internet system through the hotel's telephone system last night, I'm sure you'll appreciate that places such as this hotel have a considerable need for more advanced technology. There's going to be a whole lot more of that. All of you should be able to sit here today and run your laptop notebooks from a wireless system. That should be capable right now. We should be able to run these presentations essentially off of wireless connections directly off the internet. You don't even need to carry around those big, massive volumes of papers that is produced at IEDM and other conferences. That technology exists, so the consumer demand is going to be there. It's going to require us to have major process advancements as there's more and more demand. There's still a lot of opportunity out there. Hardware is still ahead of software. Software will catch up. That's going to require us to do more than just lithography. It's going to require the new materials that we talked about, the new architectures, the more advanced applications of manufacturing science to improve the output, improve the capability, improve the parametrics. 300 millimeter makes everything bigger, faster, cheaper. Its automation enhances the parametric capabilities. It makes it cleaner, and just in general is going to make things a whole lot better. It's a whole new retooling of the industry, and it has considerable improvements, not just in terms of the products, but the processes by which it's made. And the supply chain management must add value to address the customer needs. Must have good materials with tight process control. We must have good equipment that is available and that runs fast. Thank you very much for your time. Have a few minutes to entertain some questions.